What if the key to time travel isn't hidden in massive spaceships or theoretical wormholes, but in a realm far smaller than we can see? A world where particles can be in two places at once, defy expectations, and even communicate instantaneously across vast distances. Welcome to the quantum realm, the foundation of modern physics, and, perhaps, our best shot at unlocking the mysteries of time itself. Quantum physics isn't just about the strange behavior of the tiniest particles. It's a field brimming with possibilities, phenomena so complex and counterintuitive that they've reshaped how we think about space, matter, and, you guessed it, time. Have you heard of quantum entanglement, where two particles remain connected no matter how far apart they are? Or retrocausality, where future events could influence the past? These seemingly impossible ideas push the boundaries of what we understand about time, hinting that the rules we've always taken for granted might be far from complete. But time isn't just a scientific concept. It's something we experience every second. It flows forward relentlessly, doesn't it? Or does it? Could there be ways to slow it down, speed it up, or even reverse it entirely? The quantum realm introduces us to bizarre and thrilling possibilities, from manipulating the fabric of time itself to exploring alternate realities. If you're ready to uncover how the strangest science of today could define the future of time travel, you're in for an exciting exploration. Together, we'll break down the quantum mysteries shaping our understanding of time and venture into the possibilities they offer. Welcome to this fascinating journey into quantum physics and time travel. Time, as we understand it in our lives, feels like a straightforward concept. We wake up to the sound of an alarm clock telling us the morning hours have begun. Seconds tick, minutes pass, and hours turn into days. It is a seamless flow, a progression that we use to structure life, linear and predictable. Yet, time is more than this steady march. It is an element of the universe that, when observed under the lens of quantum mechanics, defies our intuitive understanding and challenges the very idea of what we believe it to be. What if time is not exactly what we think it is? To begin the exploration of time, it is essential to understand how it has been traditionally defined. From a physics perspective, time can be thought of as a measure of change. It is intertwined with the fabric of space-time, which acts as the stage on which the universe performs its play. This classical view of time emerged most famously through the works of Isaac Newton. Newtonian physics treated time as absolute, something universal, constant, and unchanging. Regardless of where you were in the universe or what you were doing, time ticked onward uniformly. But this understanding of time underwent a seismic shift with Einstein's theory of relativity. Einstein revealed that time is not absolute, it is relative. Time does not flow uniformly as Newton believed, but stretches and compresses depending on factors like gravity and velocity. For instance, the closer you are to a massive object, like a black hole, the slower time moves due to the immense gravitational pull. Similarly, if you were traveling at speeds near the speed of light, time would dilate, ticking more slowly relative to someone standing still. This revolutionized our understanding of time, tying it closely to the dynamics of space and motion. However, even this groundbreaking view of time is being challenged by the strange and often baffling world of quantum mechanics. Quantum mechanics alters the game entirely, introducing phenomena that are counterintuitive to the world we experience. At its core, quantum mechanics deals with probabilities and possibilities instead of certainties. Events in the quantum realm are not deterministic like they are in classical physics. They are governed by a hazy world of likelihoods. This ambiguity makes our traditional understanding of time more complex. One fundamental aspect of quantum mechanics is the uncertainty principle, which is often cited in terms of position and momentum. However, there is also a time-energy uncertainty principle. This principle suggests that the more precisely you measure one variable, for example, energy, the less precisely you can know the other, in this case, time. From this perspective, time is not quite as solid as it seemed. It is blurred and uncertain at the quantum level. Another intriguing quantum concept is superposition. A quantum particle can exist in multiple states simultaneously until it is observed or measured. This phenomenon raises fascinating questions about time. If particles can occupy multiple states, could different timelines or moments exist simultaneously as well? While this remains a speculative idea, it stirs the imagination about the nature of time and whether we experience it in its entirety or just in slices. These quantum peculiarities provide a foundation for concepts that aim to deconstruct further and rebuild our understanding of time. One such groundbreaking idea is the block universe theory. According to this view, time is not a flowing river, but a frozen block. Past, present, and future all exist simultaneously within this block. This framework shifts the perception of time from something that passes to something that simply is. Your birth, this very moment, and events in the distant future are all fixed within this frozen tapestry of space-time. Another idea posited by some physicists is that time, as we perceive it, does not fundamentally exist. Instead, it could be an emergent property, a byproduct of deeper underlying processes that we do not fully understand yet. Time, in this view, is not fundamental to the fabric of the universe. It is a kind of illusion, an emergent phenomenon that arises from the interactions of particles in our universe. Quantum entanglement, often described as spooky action at a distance, adds another layer to this time conundrum. Entangled particles remain connected regardless of how far apart they are. A change in the state of one instantly affects the other, no matter the distance. This phenomenon raises an intriguing thought. If entanglement can connect particles across vast stretches of space, could it also connect events across time? While such speculation is in its infancy, it underscores the potential for quantum mechanics to rewrite our understanding of time. Through experiments, theory, and thought-provoking speculation, quantum mechanics does not just challenge the simplicity of the classical view of time, it amplifies its complexities. Whether through the block universe, the uncertainty of quantum measurements, or the strange connectivity of entanglement, one thing is clear: time may not be as straightforward as the ticking hands of a clock suggest. Instead, it seems to be a dynamic, multifaceted component of our universe that holds secrets we are only beginning to uncover. Imagine this scenario for a moment. What if a particle could pass through a wall without breaking the wall or itself? This is not science fiction. It's quantum tunneling, a concept that's challenging everything we thought we knew about the nature of the universe. To start off, what exactly is quantum tunneling? At its core, it refers to the ability of a particle to move through an energy barrier that, based on classical physics, it shouldn't be able to surpass. Picture a person trying to climb over a hill. If they don't have enough energy to reach the top, they'd typically slide back down. However, in the quantum realm, particles don't abide by such rules. Instead of climbing over the hill, certain particles can essentially borrow energy momentarily, pass through the barrier as if it wasn't even there, and then return that energy. It's almost as if the hill was irrelevant in their path. This unsettling yet mesmerizing behavior is possible due to the probabilistic nature of quantum mechanics, where particles don't have fixed positions or paths, but instead exist as waves of probabilities. One fascinating, mind-boggling fact about quantum tunneling is that particles can transition through barriers that they seemingly wouldn't have the energy to overcome. How is this possible? On the quantum level, particles aren't stagnant. They exist in a fuzzy state where their exact position and energy cannot be pinpointed with absolute certainty. This principle comes from Heisenberg's uncertainty principle. Because of this inherent fuzziness, there's a non-zero probability that a given particle's wave function, which describes where it might be found, extends beyond the physical barrier. This probability allows the particle to tunnel through the barrier in a way that breaks all conventional rules without breaking the laws of quantum physics. Now, you might be wondering, how exactly does this manifest in the real world, and why can't we see objects around us tunneling through walls? That's an excellent question. First, quantum tunneling primarily applies to particles at extremely small scales, like electrons or photons. Large objects, like a basketball or a car, have such an infinitesimally low probability of tunneling that it's virtually impossible within the observable lifetime of the universe. This stark difference in behavior between the macro and quantum worlds stems from the scale-dependent nature of quantum effects. To better grasp how quantum tunneling works, let's look at an example. Consider electrons within an atom. These tiny particles are confined to specific energy levels, or orbits. For an electron to escape its atom, it typically needs to acquire a certain amount of energy, like heat or light, to overcome its binding force. However, under certain conditions, electrons can tunnel through the energy barrier instead of overcoming it. Without acquiring the necessary energy, they can suddenly appear on the other side of the barrier as if the barrier never existed. Why does this matter? The answer lies in the countless applications of quantum tunneling in modern science and technology. A prime example is semiconductors, the crucial components in all modern electronics. Quantum tunneling enables electrons to jump across thin barriers between semiconductor materials, playing a key role in how transistors function. These transistors are the building blocks of nearly every computer, smartphone, or electronic device you use today. Without quantum tunneling, the rapid advancement of technology we've experienced over the decades would simply not be possible. Another astonishing application of quantum tunneling relates to the workings of the sun. Deep in the sun's core, intense pressure and high temperatures cause hydrogen nuclei to fuse into helium, a process known as nuclear fusion. Classically, these particles would require much more energy than the sun's core could provide to overcome the repulsive forces between them to fuse. Yet, thanks to quantum tunneling, hydrogen nuclei can essentially bypass these barriers, allowing nuclear fusion to occur and powering the sun's ability to shine. Without it, life on Earth, as we know it, would cease to exist. Now, let's take this concept one step further. Could quantum tunneling have implications for time itself? Could particles, or even information, use this mechanism to jump through time? It's a thrilling question that has both scientists and science fiction enthusiasts buzzing. While concepts like quantum entanglement and tunneling have sparked speculation about faster-than-light travel or time manipulation, current scientific understanding remains firmly rooted in theory when it comes to this topic. Quantum tunneling has been observed countless times at the particle level, but its connection to time travel remains purely hypothetical. Theoretical models suggest intriguing possibilities, but no experimental evidence exists that would allow us to use tunneling for time manipulation. For now, the boundary between science fact and science fiction is clear. Yet, the limits of what we can imagine and understand continue to be pushed by groundbreaking research. Despite the limitations of our current understanding, quantum tunneling has solidified its place as an invaluable tool in exploring the universe. It challenges our classical worldview and gives rise to innovations that revolutionize our lives, from powering fundamental physics research to developing advanced quantum technologies. Can decisions made today influence the past? It's a question that feels lifted out of a sci-fi movie, yet it is one of the most intriguing aspects of modern physics. And no, this isn't some figment of speculative imagination. It's a reality explored through a fascinating concept in quantum mechanics known as delayed choice experiments. Strap in, because we're about to explore an area of science so counterintuitive it might just make your head spin. Delayed choice experiments are a prime example of quantum mechanics challenging the very way we perceive reality. At its core, it asks a simple yet baffling question: do the choices we make now determine how things behaved in the past? Stay with me here, because even though this concept may sound absurd at first, it has been rigorously tested and validated, creating one of the most perplexing debates in physics. To understand this better, think of the famous double-slit experiment. If you've heard about quantum mechanics before, this experiment might sound familiar. Here's a quick refresher. Imagine firing tiny particles, such as photons, at a barrier with two slits. If you place a screen behind the barrier to capture where the particles land, you'll see a peculiar result. They create an interference pattern, like waves overlapping in a pond, rather than behaving like individual particles. However, if you place detectors at the slits to see which slit a particle passes through, the interference pattern disappears. Instead, the particles act like, well, particles. This experiment is already strange enough, but physicist John Archibald Wheeler took things a step further with his proposed delayed choice experiment in the 1970s. Wheeler's idea was bold and ingenious. He asked, what if we delay the decision to observe the particle until after it has passed through the slits? Imagine that. You fire a photon at the barrier, but decide whether to detect it after it has already committed to behaving like a wave or a particle. Logic would suggest that the photon's behavior should already be determined by the time it reaches the slits. But in quantum mechanics, logic doesn't always work the way we think it should. When physicists conducted variations of Wheeler's thought experiment in real-life settings, the results were jaw-dropping, even if the decision to observe was made after the photon had passed through the slits. Its behavior still seemed to change retroactively based on that choice. If detectors were added, the photon behaved like a particle. If not, it acted like a wave. It's as if the photon knew what was coming and adjusted its actions accordingly. Now, before we go too far down the rabbit hole, it's important to clarify what this does and doesn't mean. Delayed choice experiments do not imply time travel or that we can literally rewrite the past. Instead, they reveal something profoundly strange about how quantum mechanics works. The results challenge our classical understanding of cause and effect, suggesting that, at the quantum level, events may not adhere to the linear flow of time as we experience it. Physicists interpret these findings not as evidence of particles traveling back in time, but as a demonstration of the fundamental weirdness of quantum measurement. A particle's behavior, whether it acts like a wave or a particle, isn't an intrinsic property. Instead, it depends on how we choose to measure it. This is closely related to what's known as the observer effect, which states that the act of measurement itself influences the behavior of quantum systems. What makes delayed choice experiments particularly fascinating is how they connect back to broader questions about the nature of time. Classically, we think of time as a straightforward sequence of events, past, present, and future, marching in a straight line. But delayed choice experiments hint that this may not be how time operates on a quantum scale. The future and the past may be more intertwined than we realize, though not in ways that allow causality to be violated. For instance, these findings prompt us to rethink the boundaries of what we consider cause and effect. Traditionally, cause precedes effect. Touching a stove causes a burn, not the other way around. But in the quantum realm, this sequence seems less rigid. The behavior of a quantum particle depends on the observer's actions, even if those actions occur after the particle has already made its initial state. It's a phenomenon that continues to baffle scientists and serves as a reminder that the universe operates in ways we're only beginning to understand. But what practical value does all of this have? Beyond being a mind-bending exercise in quantum theory, delayed choice experiments contribute to our understanding of the foundations of quantum mechanics, which has practical implications for technology. For instance, this research deepens our grasp of quantum measurement, a key principle behind quantum computing. Quantum computers are built on the properties of quantum bits, or qubits, which can exist in states of 0 and 1 simultaneously, a concept rooted in the same principles of uncertainty and observation that delayed choice experiments explore. Who knows? Perhaps one day, the principles uncovered through these experiments will inform technologies that we can hardly imagine today. Much like classical physics gave rise to steam engines and electricity, quantum physics is laying the groundwork for the next revolution in computing, communication, and beyond. By now, your perception of how the universe works might feel slightly unmoored, and that's okay. That's exactly what makes quantum mechanics so fascinating. Delayed choice experiments remind us that science is not just about answering questions, but also about asking better ones. What does it mean for particles to lack defined behavior until we observe them? How does quantum mechanics mesh with our everyday experiences grounded in classical physics? And perhaps, most intriguingly, what does this say about the nature of reality itself? Quantum physics often seems abstract and removed from our daily lives, relegated to laboratory experiments and theoretical papers. But every so often, phenomena like the delayed choice experiment come along, offering a glimpse into a universe far stranger and more complex than our senses might suggest. It's a humbling reminder that the ultimate answers are still out there, waiting to be discovered. And who knows, perhaps the next big breakthrough will come from someone inspired by these very concepts to see the universe in a new way. Quantum erasure, an idea that sounds pulled straight from science fiction. What if the act of erasing information could influence an event that has already happened? This is the tantalizing premise at the heart of one of quantum mechanics' most bewildering concepts. It's a phenomenon that challenges our very understanding of time, causality, and the nature of observation itself. To the untrained eye, it may seem almost magical, an experiment where the simple act of forgetting rewrites reality. However, as with all things in science, there's a deeper, logical explanation hiding in the chaos. To understand quantum erasure, it's important to first grasp which path information, a term central to quantum mechanics. Think of a classic demonstration of quantum strangeness, the double-slit experiment. A single particle, like a photon or an electron, is fired towards a barrier with two narrow slits. On the other side of this barrier is a detection screen. With no observation, the particle behaves as though it is a wave passing through both slits and producing an interference pattern on the screen. However, the moment we observe which slit the particle goes through, this wave-like behavior collapses into that of a particle, and the interference pattern disappears. This which path knowledge changes the outcome of the experiment entirely. Simply knowing whether by placing some sort of detector by the slits collapses the possibilities into a single, clear event. Now imagine that we erase the which path information. What happens then? This is where quantum erasure steps onto the stage. If the information about which slit the particle travels through is sealed away or destroyed after the particle travels, but before its final result is observed, the wave-like behavior and interference pattern can return, as though the particle forgot which path it took. This act of erasure, not observing which path info, seems to unlock the particle from its constrained behavior. But here's the twist that elevates quantum erasure from peculiar to mind-bending. The erasure doesn't even need to occur in real time. It can happen after the particle has hit the detection screen, leading to a delayed choice quantum eraser experiment. A real-world example of this is the delayed choice quantum eraser experiment. Here, particles are emitted and pass through a double-slit barrier. But this time, the experimental setup includes paired photons. One photon, known as the signal photon, travels to a detector. Meanwhile, the paired photon, called the idler photon, takes a different path to a secondary detector. Here's the kicker. The information about which slit the signal photon traveled through can be inferred based on the idler photon's path in some branches of this setup. However, if this which path information is erased, say, by routing the idler photons in such a way that this information becomes unknowable, the interference pattern can reappear in the signal photons. And remember, this decision to erase the information can come after the signal photons have already hit the detector. It's as if the future, the act of erasing the information, reaches backward in time to influence the particle's behavior during its earlier flight. If this sounds suspiciously close to time travel, that's understandable. However, quantum mechanics doesn't actually break causality or allow for retroactive rewriting of history. The trick lies in the intertwining nature of entangled quantum particles and their shared wave function. Once you account for how all pieces of the system interact, you see that quantum erasure doesn't rewrite the past. Instead, it tells a consistent story across time and space where the results align perfectly with current observations, creating an illusion of retroactivity. Quantum erasure also provides an unparalleled lens for understanding one of quantum mechanics' more elusive principles: entanglement. When particles are entangled, their properties are linked so intimately that the measurement of one instantly determines the properties of the other, no matter how far apart they are in space. The delayed choice quantum eraser exploits this connection. It showcases how entanglement and the collapse of probabilities into fixed outcomes behave in ways that unsettle our ingrained understanding of cause and effect. It's like a cosmic magician, showing us one thing while hiding the mechanisms behind the curtain. The possible applications of this principle, though purely theoretical at this stage, ignite the imagination. Quantum erasure could allow breakthroughs in our understanding of quantum information manipulation. It might prove relevant to quantum memory mechanisms, where erasing and rewriting entangled states play critical roles. Quantum computers, which rely heavily on controlling particle states and information, could also tap into principles adjacent to erasure setups. And in quantum communication, erasure schemes might help refine how quantum information encoded in particles is managed and transmitted securely. However, these ideas remain speculative. While quantum mechanics is a feast for the mind, reality often tempers our more ambitious goals. Yet, despite its complexities, quantum erasure holds an enchanting allure. It reveals cracks in our classical worldview, hinting at a universe governed by rules far more subtle, strange, and interconnected than we could have imagined. For every answer it seems to offer, it leaves many more questions awaiting those who dare to explore its paradoxical depths. This tension between uncertainty and clarity, the known and the unknown, is what makes quantum physics and concepts like quantum erasure so irresistibly fascinating. What if the choices you make tomorrow could ripple backward and alter the outcomes of yesterday? What if the decisions yet to be made already hold sway over the events you thought were set in stone? These aren't abstract musings from the realm of science fiction, but rather fascinating questions born from the intricate study of quantum physics. This is retrocausality, a mind-bending concept that challenges our most basic understanding of cause and effect, shaking the very foundations of time as we perceive it. At its core, retrocausality suggests something profoundly unsettling yet exhilarating. It entertains the possibility that time, a construct we often imagine as a straight, unyielding arrow, might be more like a flowing river, capable of bending, doubling back, or even blurring its boundaries entirely. Retrocausality introduces the idea that causation isn't necessarily one-directional. Future events might echo back to influence the past, intertwining timelines in a way that defies our classical intuition. This concept might sound like philosophical speculation, but its roots lie firmly in the domain of cutting-edge quantum mechanics. Within this field, the very nature of time becomes nebulous and flexible. Using quantum mechanics as its backdrop, retrocausality asks a question that might seem absurd in the context of our everyday experiences. Could the act of observing or measuring something in the future have a retroactive effect on its earlier state? At first glance, our everyday experiences scream no. You drop a coffee cup, and it shatters on the floor. You can't look at the shards 10 minutes later and miraculously reshape them into a pristine cup by imagining the fall didn't happen. Our world treats time as linear. One event leads to the next, and effects follow causes in a predictable march. But when you zoom down to the quantum level, the rules that govern cause and effect suddenly feel less immutable. Retrocausality finds its most interesting playground in light's tiniest particles, photons. Imagine a particle of light behaving differently, depending on something that happens to it after it's already been emitted. If you think that sounds outrageous, you're not alone. It's the kind of discovery that makes researchers scratch their heads, and physicists rethink centuries-old assumptions about the mechanics of the universe. Take, for instance, the experiments surrounding quantum entanglement. Picture a pair of entangled photons, two particles linked in such a way that the state of one directly affects the state of the other, no matter how far apart they are. But it gets stranger. When we choose to measure one entangled photon's polarity in the present, it seems to retroactively determine the state of its partner photon, even if that partner state existed in the past. It's as though information about future measurements travels backward through time to resolve the ambiguity of the pair's behavior. Even more surreal is the delayed choice quantum eraser experiment. This study involves splitting and recombining photon beams to explore how their behavior changes based on whether a scientist decides to observe them. Here's the twist. A decision made in the future about whether to observe the photons seems to retroactively dictate whether they travel as particles or interfere as waves in the past. The past, which many of us imagine as a fixed and unchangeable record, appears oddly pliable in these experiments. But hold on. Before we get ahead of ourselves and imagine a reality where revisiting past mistakes becomes as easy as editing a Word document, retrocausality has its limits. Its applications and implications, so far, remain firmly rooted within the quantum world. This isn't about rewriting personal history or time traveling to correct global injustices. There are no futuristic scenes of scientists zipping through wormholes to meddle with historical events. Instead, retrocausality touches on subtle behaviors of particles at minuscule scales, nudging us closer to unraveling the mysteries of time and causality itself. Where does this leave us now? Retrocausality is still an active frontier of research, a bold yet delicate idea that physicists continue to test, question, and refine. At this stage, its practical applications may feel like whispers of a yet-to-arrive future. The role of retrocausality in classical systems, systems that govern the macroscopic world we live in, remains speculative at best. Still, The broader implications for quantum mechanics and how we interpret the nature of time are impossible to ignore. Could retrocausality ultimately reshape how we build theories of the universe? How might it alter the frameworks through which we view reality, causality, and existence itself? The pursuit of these answers is more than an intellectual exercise. It's a testament to the human capacity to question what once seemed unquestionable. Quantum physics often feels like a puzzle you can't quite finish, each piece promising a glimpse of the bigger picture. But the edges never quite aligning. Among its many mysteries is the question that has confounded physicists and philosophers alike for decades. What happens when we measure something at its tiniest scale? The quantum level. Imagine flipping a coin. It lands heads or tails, there's no in-between. But in the quantum world, particles exist in multiple states at once, only choosing a state when observed. How does something so strange fit into our understanding of the universe? This is where a bold, game-changing idea enters the story, one that could entirely change how we think about reality itself. Enter Hugh Everett and his many worlds interpretation. It's the 1950s. Quantum mechanics has already revolutionized our view of the microscopic universe. But even its most brilliant pioneers struggle to explain certain phenomena. Hugh Everett, then a young doctoral student at Princeton, proposes something audacious. What if every quantum event creates a new universe? Picture this for a moment. Flip that coin again. Instead of just landing on heads or tails, the very act of flipping it splits reality in two. One universe exists where it lands heads, and another where it lands tails. Each represents a different outcome, neither one more real than the other. Everett's idea, later coined the many worlds interpretation, defied the conventional thinking of his time. Instead of collapsing into a single outcome like a wave crashing against the shore, the quantum wave function never collapses. Instead, it branches endlessly, creating parallel universes for every possibility. The implications of this theory are mind-blowing. Think about your daily life and the countless decisions you make. Should I take the scenic route or stick to the main road? Should I accept that new job offer or stay in my current role? According to Everett, every choice you make spawns a new universe, one where you chose differently. Somewhere out there, another version of you is living an entirely different reality. Maybe in one universe, you're an artist in Paris. In another, a CEO in Tokyo. The idea is equal parts exhilarating and dizzying, challenging our most basic assumptions about the nature of existence. But how does this theory change our understanding of something even wilder, time travel? The many worlds interpretation opens up possibilities that traditional, single-universe thinking could never entertain. Imagine you invent a time machine and travel back to visit your past self. Instead of altering your own timeline and risking paradoxes, the infamous grandfather paradox, for instance, where your interference could prevent your own birth, you'd simply jump to a universe where events naturally unfold based on your actions. Picture it this way. You miss an important deadline at work and wish you could reverse time to meet it. Rather than rewinding the clock on your original timeline, the many worlds interpretation suggests you could move to a universe where you did meet the deadline. Your original timeline remains untouched while you begin anew in an alternate reality. This reshapes the age-old concept of paradoxes. In the grandfather paradox, if you traveled to the past and prevented your grandfather from meeting your grandmother, how could you exist to make the trip to begin with? The many worlds interpretation resolves this conundrum. By preventing the meeting, you create a new universe where you were never born, but your original universe and your existence within it remains intact. It's not so much changing the past as it is choosing a different thread in the infinite fabric of existence. This makes time travel less of a disruption and more of a detour, seamlessly sidestepping the philosophical headaches that have plagued the idea for centuries. Yet, the theory doesn't come without its complexities and challenges. For one, can we still call it time travel if you're unable to return to your original timeline? This brings up another question. How would we even pinpoint the exact universe we want to jump to? The vastness of possibilities, while exciting, makes it equally daunting. Imagine trying to find a specific grain of sand on an endless beach. Scientists have also yet to determine if these alternate universes are anything more than mathematical constructs. Without physical evidence or a way to interact with these other realities, could they remain forever speculative? The many worlds interpretation, for all its elegance, leaves us grappling with as many questions as it answers. Time travel, alternate realities, quantum pathways, these ideas ignite our imagination like few others can. Yet, they also invite us to confront the very limits of our understanding, forcing us to reconsider everything we think we know about time, choice, and existence. The many worlds interpretation is not just a scientific proposition, it's a mind-expanding lens through which to view our universe. And maybe, just maybe, it's the closest we've come to peeking behind the curtain of reality itself. Imagine a world where time isn't linear, where the future doesn't merely follow the past, and where the boundaries of causality blur into a surreal dance of possibilities. This isn't the opening to a science fiction blockbuster, it's the foundation of a mind-bending concept in physics called closed time-like curves. Rooted in the equations of general relativity, these theoretical pathways propose that space-time may bend and fold upon itself, allowing for loops in time. While its foundations lie in Einstein's groundbreaking work, the implications of closed time-like curves extend far beyond the realm of classical physics, intersecting with the enigmatic principles of quantum mechanics. Today we'll illuminate this fascinating intersection while focusing on scientifically grounded theories, steering clear of speculative fiction for a tour through a universe stranger and more compelling than any movie script. Closed time-like curves find their origins in Einstein's general theory of relativity. This revolutionary framework describes how massive objects influence space-time, warping it like a bowling ball on a rubber sheet. Fascinatingly, under specific mathematical conditions, this warping of space-time could theoretically allow for loops, where the timeline bends and reconnects to itself. Imagine tracing a path in space-time that brings you back to your starting point, not in space, but in time itself. Such pathways imply the possibility of returning to earlier moments or even coexisting with past versions of oneself. One notable early proponent, Kurt Gödel, proposed a rotating universe solution where such loops could naturally arise. Similarly, Frank Tipler explored the theoretical construct of Tipler cylinders, infinitely long rotating objects purported to generate these time loops. These models, while thrilling for the imagination, raise fundamental questions about nature's willingness to accommodate time loops within its physical laws. Beyond their theoretical elegance, closed time-like curves raise provocative questions about time travel. If a pathway through time exists, could an object or a person journey to their own past? This possibility opens the door to paradoxes that challenge our intuition. Take the grandfather paradox, for example. A time traveler who interferes with past events, such as preventing their grandparents from meeting, risks erasing their own existence, a contradiction that seems to defy logic. Yet the mathematics of general relativity offers no explicit prohibition against such loops, leaving physicists to grapple with whether they represent a flaw in our understanding of time or a deeper truth about the cosmos. However, creating the physical conditions for closed time-like curves isn't simple. Theoretical models suggest the need for exotic matter with negative energy density, a type of substance that defies conventional physics. While some aspects of negative energy have been tentatively explored in quantum mechanics, its existence remains speculative at best. The energy requirements for bending spacetime into a loop are astronomically high, far beyond anything our current technology could achieve. This is where the principles of quantum mechanics provide an intriguing avenue of exploration. Unlike the deterministic framework of classical physics, quantum mechanics introduces probabilities and uncertainties, offering a drastically different canvas for studying systems with closed time-like curves. It's here that the concept of quantum self-consistency comes into play, suggesting that closed time-like curves could avoid paradoxes by adhering to probabilistic rules rather than deterministic ones. The Deutsch model, named after physicist David Deutsch, illustrates how quantum mechanics could reconcile these loops. According to this model, events within a closed time-like curve can influence their own past in a way that avoids logical inconsistencies. Each interaction within the loop must self-consistently support the conditions that created it, offering a tantalizing glimpse into a paradox-free framework for time travel. For example, quantum particles traveling through time might interact with past versions of themselves, ensuring that the outcomes align perfectly without breaking causality. Such concepts aren't merely theoretical musings, but have inspired computational simulations and studies to model the behavior of particles in closed time-like curves. Researchers have run experiments to examine how quantum systems might behave if subjected to time loop-like conditions. The results suggest an elegant consistency. For instance, particles might interfere with their past iterations in a manner that obeys the laws of quantum mechanics while preserving their physical properties. These findings bolster the idea that, under the probabilistic umbrella of quantum physics, the seeming contradictions associated with closed time-like curves may dissolve. What's even more fascinating is the potential role of these principles in advancing fields like quantum information and computation. Hypothetical quantum systems that incorporate closed time-like curves appear to solve certain computational problems exponentially faster than classical systems, providing a tantalizing glimpse into applications that extend far beyond theoretical physics. However, as captivating as these ideas sound, the challenges associated with closed time-like curves are formidable. To date, no experimental evidence substantiates their existence. The solutions proposed by Gödel, Tipler, and others remain within the realm of mathematical constructs, tethered to highly specific and often unrealistic conditions. Our technological capacity to manipulate space-time, which would require harnessing exotic matter or achieving energies on a cosmic scale, is nowhere close to the needs of these theoretical models. Even within quantum mechanics, while simulations and theoretical frameworks suggest tantalizing possibilities, practical implementation remains light years away. These considerations underline a humbling truth about our current understanding of closed, time-like curves. While they may provide a fertile ground for exploring the boundaries of physics, any real-world applications are likely to lie well into the distant future, serving as reminders of the vast gaps in our comprehension of the universe. And yet, within these gaps lies inspiration. The study of closed, time-like curves stretches far beyond the ambition of unraveling time loops. It compels physicists to rethink the fundamental laws governing space, time, and causality, forcing them to confront the enigma of how macroscopic systems interact with probabilistic quantum phenomena. Through these inquiries, physicists are expanding the landscape of human knowledge, unlocking profound insights into the nature of reality itself. Whether by refining theories of general relativity, advancing quantum computation, or revolutionizing cosmology, research into closed time-like curves creates ripples across multiple disciplines, shaping the trajectory of scientific discovery. Each exploration brings us closer to answering foundational questions that have defined human curiosity for millennia, offering a bold reminder of the audacity and wonder at the heart of scientific exploration. Time travel has been a source of human fascination for centuries. From wild tales of stepping into other eras to intricate theories exploring its scientific plausibility, it has continuously sparked our imaginations. The allure of breaking free from the confines of time, traversing into the past to witness history, or stepping into the future to glimpse potential outcomes, is irresistible. But how close are we to turning this dream into a reality? Are we merely indulging in fiction, or does science hold a blueprint for what could become the greatest technological breakthrough in human history? Today, we will explore one of the most ambitious frontiers in theoretical physics, constructing a quantum time machine. To grasp the essence of this potential achievement, one must first understand the theoretical foundation behind time travel, grounded in Einstein's groundbreaking theory of general relativity. This theory describes space-time as a vast, flexible fabric that warps and bends under the influence of mass and gravity. Picture space-time as a stretched rubber sheet. Placing a massive object like a bowling ball creates a dip, causing smaller objects to roll toward it. Now, imagine creating a space so distorted that it curves back on itself, connecting distant points across it. This is no mere thought experiment. It is the theoretical underpinning of the wormhole, a conduit capable of linking separate moments in time and space. Wormholes, often termed Einstein-Rosen bridges, are speculative constructs that offer a passage through space-time. Imagine a tunnel connecting two otherwise distant points, a shortcut through the universe. Sounds simple enough, right? But the reality of creating or stabilizing such a bridge is staggeringly complex. Wormholes are predicted to be inherently unstable, prone to collapse almost instantly after forming. For one to be traversable, it would need a mechanism to hold it open. Enter exotic matter, a hypothesized form of matter with negative energy density that could counteract the natural forces seeking to collapse the wormhole. But exotic matter is no ordinary substance. Its very existence defies the conventional understanding of physics, and creating or harnessing it remains one of the biggest challenges of this endeavor. The focus now shifts to quantum physics, which promises potential solutions to these hurdles. At the heart of quantum mechanics lies the concept of quantum fluctuations, the ephemeral and energetic ripples occurring even in a vacuum. These fluctuations give rise to negative energy, a crucial ingredient for stabilizing wormholes. Quantum systems, with their paradoxical behavior and vast computational potential, may hold the key to generating and managing negative energy on a scale grand enough to support these space-time conduits. One example is the Casimir effect, a phenomenon in which two closely placed, uncharged parallel plates experience an attractive force caused by quantum vacuum fluctuations. This effect manifests as a direct demonstration of negative energy in action. If such quantum phenomena can be scaled to larger systems, they could theoretically contribute to the stabilization of wormholes. Attempts to harness this energy require leaps of imagination and experimental ingenuity. While the Casimir effect works as a laboratory-scale demonstration, converting it into a functional energy source to hold space-time open would demand unprecedented advancements in quantum field manipulation. If quantum systems appear poised to offer solutions, quantum computing might offer the means to model and test these possibilities. Unlike traditional computers, quantum computers use qubits, which don't confine themselves to binary states. They enable simultaneous computation across enormous potential outcomes, allowing for breakthroughs in modeling complex phenomena. Quantum computing allows researchers to simulate the curvature of space-time, laying the groundwork for understanding how warping spacetime may work in a controlled and predictive manner. For instance, theoretical proposals in quantum gravity, linking the smallest quantum scales to Einstein's larger relativistic picture, are becoming computationally approachable through quantum systems. While still in its infancy, such work demonstrates the potential of quantum computations in not just understanding, but eventually manipulating space-time foundational elements. Shifting gears, one of the most captivating developments in quantum physics is the discovery of time crystals. Unlike regular crystals, which repeat their structures in space, time crystals show oscillations that defy one of physics' cardinal rules: energy conservation over time. Time crystals oscillate perpetually between states without losing energy, providing a phenomenon previously thought impossible. Now consider the implications here for time manipulation. Imagine a system capable of creating stable, repeating loops not just in space, but potentially in temporal dimensions as well. The creation of time loops might allow localized regions where temporal rules bend or fragment, introducing new possibilities for anchoring or guiding wormholes, or sustaining controlled space-time anomalies. Practical applications of time crystals remain speculative but thrilling. Recent laboratory experiments have succeeded in demonstrating the existence of time crystals under strictly controlled settings, a stepping stone to exploring their functional potential. One of the most tantalizing ideas is the use of time crystals to stabilize unstable time phenomena, offering a sustaining mechanism for localized temporal loops necessary for entry points into alternate moments on the space-time continuum. Such ideas are, for now, far from implementation, but suggest a future rich in experimentation and discovery. Another quantum phenomenon playing its part in these theories is quantum teleportation. On its surface, teleportation describes the instantaneous transfer of quantum states between 2 points using entangled particles. Entanglement, a core feature of quantum mechanics, describes particles intrinsically linked no matter the physical distance between them. Transferring data or states across space comes with fascinating implications for temporal mechanics. What if two entangled particles could connect across time rather than just space? While current research into quantum teleportation focuses on classical data transfer, some physicists are exploring the possibility of modifying this to explore time entanglement. Linking quantum systems, not by spatial distance but by temporal separation, requires mathematical rigor and wholly reimagines the constraints of both time and causality. Imagine, then, that entanglement is no longer bound to simultaneous points in space, but can bridge temporal distances. Entangling a current particle state with a state that existed days or centuries before could open theoretical corridors of interaction across time. Such ideas remain so new that they ignite debate over both feasibility and desirability. Could altering the inherent symmetry of time lead to paradoxes? Would these efforts, if advanced, be bound by their limits or released from restrictions entirely? Though these questions currently lack definitive answers, they form an irresistible avenue for future exploration. When considered together, concepts like wormhole stabilization, quantum fluctuations, advanced computing, time crystals, and quantum teleportation each represent pieces of a dizzyingly complex puzzle. They embody humankind's relentless pursuit of understanding and reshaping its place in both the cosmos and the continuum of time. These advancements demand integration, as no single area holds the definitive answer to building what could truly be called a time machine. Instead, their collective progress steps toward peeling away layer after layer of mystery surrounding space-time manipulation. Time travel is one of the most fascinating concepts in science fiction, offering a tantalizing glimpse into a world where the boundaries of past, present and future blur. But could it move beyond the realm of fantasy into scientific reality? Some of the most brilliant minds in quantum mechanics suggest it might not be as impossible as it seems. Imagine a universe where manipulating tiny particles could give us unprecedented control over the fabric of space-time itself. Could quantum mechanics hold the key to time travel? This question, once confined to speculative novels and Hollywood blockbusters, has now begun to permeate the academic world, driven by new discoveries in the intricate relationships between quantum entanglement and the structure of space-time. To explore this, we need to understand the extraordinary phenomena of quantum entanglement. Quantum entanglement occurs when two particles interact in such a way that the state of one particle becomes instantly connected to the state of the other, no matter how far apart they are. It's almost as though the universe has given these pairs of particles a private line of communication. This extraordinary behavior has been called spooky action at a distance, a term coined by none other than Albert Einstein himself. At first glance, this defies common sense. How could one particle instantly know what its entangled twin is doing across vast distances? Yet experiments have repeatedly confirmed this baffling connection, pushing the limits of what we understand about the laws governing the universe. Imagine splitting a pair of gloves, one left-handed and the other right-handed, and sending them to opposite ends of the Earth. The moment you open one box and see the left glove, you'll instantly know the other box contains the right one. But here's the catch that makes entanglement so extraordinary. Quantum particles don't just know their state beforehand. The act of measuring one particle influences the state of the other at that exact moment. It's as though the particles are perpetually locked in an invisible dance, perfectly synchronized in ways we don't yet fully comprehend. Now, the conversation gets even more interesting when we bring Einstein's theory of general relativity into the equation. General relativity describes the universe as a four-dimensional fabric of space-time, where massive objects like planets and stars warp this fabric, creating the force we call gravity. Within this framework lies the concept of wormholes, also known as Einstein-Rosen bridges. These wormholes are hypothetical tunnels through space-time, potentially linking two distant locations or even different points in time. Think of space-time as a two-dimensional sheet of paper. If you fold the paper so 2 points touch and then punch a hole through it, you've created a shortcut. Wormholes, in theory, could function in a similar way on a cosmic scale. Why is this relevant to entanglement? Enter the groundbreaking concept known as the EREPR conjecture. Named after Einstein, Nathan Rosen, and pioneers of early quantum mechanics, this conjecture posits that the mysterious connections between entangled particles and the structure of wormholes, the hypothetical shortcuts through space-time, it might actually be two sides of the same coin. Essentially, it suggests that every pair of entangled particles could be connected by a microscopic wormhole. It's a mind-bending idea, but one that hints at a deeper unity between the laws governing the vast cosmos and the enigmatic quantum world. To grasp the EREPR conjecture, think of space-time as a fabric full of tiny threads. Each thread represents the connection between two entangled particles. If you were to follow a thread from one particle to the other, it might loop through a tiny wormhole. Does this mean you could use entanglement to travel backward or forward in time through these wormholes? Not so fast. While the conjecture provides a theoretical framework linking two of the biggest puzzles in physics, quantum mechanics and general relativity, it's still just that, a theory. Experimentally verifying such an idea remains one of the most formidable challenges in modern physics. The link between entanglement and space-time stretches far beyond theoretical conjectures and into the realm of advanced experiments. Groundbreaking technologies, such as quantum processors, have enabled scientists to simulate and explore these connections like never before. For instance, researchers have used entangled photons to test whether manipulating one particle has any measurable influence on space-time geometry. Early insights hint that entanglement could indeed affect the underlying structure of the universe, but much work remains to be done to confirm these findings. Imagine having the tools to probe the very fabric of existence itself, a capability that feels closer to magic than science. And yet, significant hurdles lie ahead. For one, creating and maintaining entanglement on the scales required to test the ER-EPR conjecture is a colossal technological challenge. The fragility of quantum states, which can be disrupted by even the slightest environmental interference, means these experiments require exceedingly precise conditions and equipment. Additionally, while we can simulate some aspects of quantum mechanics and general relativity using advanced models and algorithms, there's currently no practical way to manipulate entangled particles to create or identify wormholes. Still, the potential implications are too enticing to ignore. If entanglement and space-time are indeed linked, could we one day manipulate this connection to create shortcuts through the universe or even through time? This idea is rooted in speculation, but is not entirely without merit. For example, some physicists theorize that if we could somehow stabilize and control the connections represented by the ER-EPR conjecture, we might gain limited access to regions of spacetime that would otherwise be unreachable. It's a wild and tantalizing possibility to consider. Of course, the idea of using entanglement to enable time travel raises countless philosophical and scientific questions. Could we travel into the past without creating paradoxes? Would future civilizations appear to deliver pioneering technologies or issue warnings about the misuse of such power? While these questions may lean toward science fiction, they underscore the profound implications of exploring these concepts. The mere act of questioning drives us closer to the answers. Quantum entanglement is a phenomenon that holds the key to some of the most puzzling mysteries of the universe. It is a concept that has intrigued scientists and enthusiasts alike, sparking curiosity about its role in space-time, time travel, and the nature of reality itself. Beginning with the notion that entangled particles communicate instantly across vast distances, violating classical constraints of locality, we stand at the precipice of a deeper understanding of how the universe behaves, not just spatially, but temporally. The idea of using quantum systems to explore time travel is no longer confined to the realms of science fiction. Recent advancements have brought us closer to simulating scenarios that were once deemed impossible. Imagine a particle traveling backwards in time through a closed, time-like curve, a concept proposed in Einstein's theory of general relativity. This raises profound questions. Could this lead to paradoxes like the grandfather paradox, in which the particle alters events in its own past, essentially rewriting its own history? Quantum simulation, however, reveals a potential resolution. By leveraging quantum systems, scientists have found ways to simulate such time travel scenarios while evading traditional paradoxes through the mechanics of quantum entanglement and superposition. IBM and Google, two titans in quantum computing, have taken considerable strides in simulating these quantum mechanics. Using their quantum processors, both teams have successfully modeled particles, navigating closed time-like curves, thereby shedding light on how such systems behave under varying conditions. IBM's quantum computers, for example, have been deployed to simulate retrocausal systems, where causes and effects appear to reverse roles. Through these simulations, researchers have observed how particles choose their states without violating the fundamental principles of quantum mechanics. The particles maintain consistency in their behavior, suggesting that retrocausality might not create contradictions, but rather it could operate within a framework yet to be fully understood. Similarly, Google's quantum team pushed boundaries by running experiments to analyze the intricate dynamics of entanglement across time. By recreating scenarios where particles might interact with their past or future selves, the team revealed insights that challenge our traditional notions of linear time. The implications are vast. If particles can influence their past states without creating paradoxes, could this hint at a new way of interpreting the arrow of time itself? These experiments don't just act as proofs of concept. They expand the horizon of what may be technologically and theoretically possible in the years ahead. The concept of retrocausality naturally attracts skepticism, but the advances in modeling retrocausal systems are turning the skepticism into fascination. Retrocausality is the notion that effects can precede their causes, inverting our classical understanding of cause and effect norms. Through advanced quantum simulations, researchers now have tools that allow them to test these mind-bending hypotheses in controlled environments. For instance, models suggest that particles operating under retrocausal influences could still remain consistent with the overall system's integrity. They exhibit behaviors that appear to anticipate future outcomes without eroding the stability of the quantum state. Such findings fuel the idea that retrocausality isn't necessarily a violation of the natural world, but quite possibly an inherent feature of spacetime's quantum fabric. A fascinating aspect of these discoveries is the way quantum systems inherently circumvent paradoxes. Unlike classical systems, where altering the past inevitably leads to inconsistencies, quantum systems seem to adapt dynamically. The superposition principle allows particles to exist in multiple states simultaneously until they are observed. This flexibility could explain how particles avoid contradictions when looping through time. Picture this as a quantum choose-your-own-adventure story. Particles might explore multiple paths through time, but only the ones that maintain system consistency survive. This elegant solution demonstrates the resilience of quantum mechanics and its ability to transcend classical limitations. The role of entanglement in these scenarios cannot be overstated. When particles become entangled, their properties become interconnected regardless of the distance separating them. This entanglement persists even when one of the particles is subjected to interactions that simulate time travel. Research indicates that entangled states might hold the key to enforcing consistency across temporal interactions. It's as if the particles, through entanglement, communicate to ensure that their shared quantum state remains invariant, further reinforcing the system's stability. This interconnectedness raises deeper questions about whether time itself might be an emergent property arising from the quantum state of the universe. The interface of quantum computing with these theoretical frameworks has enabled a new era of exploration. Companies like IBM and Google are not just pushing the technical boundaries of quantum hardware, they are providing the tools to probe the philosophical questions that have confounded humanity for centuries. Their quantum processors can handle complex computations that would take classical supercomputers millennia to complete, allowing researchers to simulate interactions and entanglements on an unprecedented scale. These simulations offer glimpses into the mechanisms that could define time travel and retrocausality in the real world. Furthermore, as researchers deepen their understanding of quantum systems, they expose the limitations of classical physics. Traditional models fail to account for the nuances of time and causality revealed through quantum mechanics. The quantum realm operates on principles that often appear counterintuitive, forcing us to rethink the very foundations of reality. Energy states fluctuate, particles behave probabilistically, and information seems to flow in ways that defy macroscopic intuitions. Time, as perceived in our everyday experience, may just be one of many dimensions. Its apparent linearity a consequence of the scale at which humans operate. Within the quantum domain, time may loop, branch, or even dissolve entirely, creating a tapestry of temporal possibilities. Another intriguing outcome of these advancements is their potential to unify previously disparate approaches to understanding space-time. Theories attempting to reconcile general relativity with quantum mechanics have historically faced challenges, particularly concerning how gravity interacts at quantum scales. However, the exploration of entanglement and retrocausality introduces novel frameworks that could bridge these gaps. Some researchers hypothesize that space-time itself may emerge from the entangled structures of quantum states. If true, this realization could provide a pathway to a long-sought theory of quantum gravity.